Hi, hello everyone. Good evening, all of you. How are you all doing? I hope all are doing well. Anyway, warm welcome all of you to the Infinity Learn JEE YouTube channel. This is me Surya, your chemistry faculty from Infinity Learn. Hi Anish, good evening. Okay, let's get quickly started. Today in this particular session, we are going to discuss the next topic, right? From the same chapter, chemical bonding and molecular structure. Let us quickly started about the valence bond theory, right? Okay, so far we discussed about the VSEPR theory, Causal-Lewis approach, everything, right? Yes. Okay, in this session we are going to discuss detailing about the valence bond theory. It is shortly known as VBT. Okay, the valence bond theory was proposed by Hitler and London, and it's later modified by Linus Pauling, right? This is the history of the valence bond theory. Now let us discuss about what are the major postulates of the valence bond theory. Let us see one by one. Okay, these are the main 4 postulates of the valence bond theory. The first one discuss about that a covalent bond. We have discussed about the covalent bond, right? In the case of covalent bond, according to valence bond theory, it is formed by the overlap of atomic orbitals. What? Overlapping of atomic orbitals, right? So this is a major concept behind the valence bond theory. We can call it as orbital overlapping concept. Right? Valence bond theory, according to the valence bond theory, a covalent bond is formed by the overlap of atomic orbitals of valence shell of the 2 atoms. Of valence shell of the 2 atoms. Then this is the first concept. Then which orbital will undergo overlapping? This is the concept, right? Only half-filled atomic orbitals. For example, if I am containing any of the atomic orbital, it having unpaired electron, one unpaired electron will undergo the overlapping having the opposite spin. You will be discussing later by using the examples also. Then here we have to identify how the overlapping affects, right? The greater the extent of overlapping, there will be the strength of bond also increases. What is the third postulate? The greater the extent of overlapping, the strength of covalent bond formed is also increases, right? Then the last point of the valence bond theory is that the bonds that are formed mostly in the direction of electron clouds, right? Direction in which the electron clouds are concentrated. Just memorize this postulates detailing, then you will be explaining with the use of valence bond theory by taking the examples, right? Clear? The postulates are clear for everyone? Just let me know. Yes. Now let us go to the what do you mean by the orbital overlap concept. Fine. In the case of overlapping, there will be different types, right? Depending upon the types of overlapping, there will be 3 types. One is the positive overlapping, the second one it is negative overlapping, and third one it is zero overlapping. Okay, let us see what is the positive overlapping. I hope everyone had the idea about the atomic orbitals, right? You have already studied in your second chapter, that is the structure of atom. You must have an idea about the shape of s orbital, right? For example, if I am taking s orbital is always having the shape of spherical, in the shape of a sphere, right? So if I am considering the s orbital here, I will be giving the sign of plus, right? You have already studied in your structure of atom chapter about the sign of the orbitals, right? There will be plus minus sign. It will depends on the sine wave function, right? Psi wave function. This will denote the phase of orbital, right? Phase of orbital. Now, in order to get the positive overlapping or the complete bond formation, there are some conditions to be satisfied, right? The first condition is that orbitals should be in the same phase. orbitals are in the same phase. For example, if I am taking in the case of positive or negative, right? If the two orbitals are in the plus plus sign, otherwise minus signs, it will be in the same phase. In that particular case, there will be the overlapping happens. For example, if I am taking an orbital of here, this is our s orbital, right? Having this sign of plus here. Now, if I am taking a p orbital, right? Plus minus, right? In the case of here, both the sides are plus plus, which means it is in the same phase, right? Clear? It is in the same phase. There will be the overlapping happens. So we can draw like this. This is the region where the overlapping happens, right? This plus plus region will overlap here. Then it will form the SP overlapping. This overlapping is known as the positive overlapping. Clear? Now, if I am taking the another condition, the same s orbital, right? These two s orbital. What will be the overlapping here? Is it positive, negative, or anything else? Both are in the same sign because they are in the same phase. So it will have the overlapping of this side, right? Same phase, it will overlap like this. So it will form this is the overlap region, right? So this is the positive overlapping of SS overlapping. Clear? Okay, what is the condition for an orbital having the positive overlapping? It should be in the same phase. Then also it should be in the same orientation also. As you can see here, these spherical shape are in the same orientation, right? Same side, right? Now, if I am taking another condition, that is Px, right? I hope everyone familiar with this shape of the p orbitals also, dumbbell shape, right? So this will be our internuclear axis, the imaginary line drawing through the nucleus of the two orbitals. So this is the internuclear axis. If I am taking this as a z axis, this will be the either px or py, right? If I am taking here, it is px. What will be the overlapping here? These are both are the plus sign. What will be the overlapping here? This is the overlapping, right? This is a PP positive overlapping. Clear? The major condition to form the positive overlapping is that it should be in the same phase, whether it is in plus or minus. Even also, you can form the bond same like this if it is have the negative sign also, right? If it is both are in the negative sign also, you will form the positive overlapping. Clear? Then the next condition is that, what do you mean by the negative overlapping? What do you mean by the negative overlapping? Just opposite to that, right? Orientation will be same, but the phase will be different. So we will call it as an out of phase, right? We will be calling it as out of phase if I am taking the negative overlapping. Otherwise, it is also known as out of phase, which means that opposite phases, right? Plus minus with the same orientation. Then it will form the negative overlapping. Whether it is plus, then the next one it is minus, right? Just opposite. One will be positive sign, another one will be negative sign, right? Then overlapping will also happen here, but we will call this overlapping as negative overlapping. Then you can use this also. If you are taking py orbital, py or px, plus minus, plus minus. Then here it is there is no any overlapping, right? There is no any positive overlapping. There will be the overlapping of negative, right? Again, this is a negative overlapping. Then I have a question for you. If you are taking two spherical s orbital, is there any chance to form the negative overlapping? If you are taking two spherical s orbital, is there any chance to form negative overlapping? Any idea or any guess? Yes or no? Okay, you must have an idea about the shape of the orbital. If we are considering the s orbital now, it will be complete spherical, which means that the complete cloud is there. We will take it as a positive orbital, right? In the case of negative overlapping, it should be out of phase, which means that both the orbitals have different phase. But if one is plus, then another will be negative, right? So, in the case of s orbital, there will be any chance of negative overlapping. Clear? Yes. Next one is the third concept, that is zero overlapping. Zero overlapping. If we are considering the positive and negative overlapping, we will contain it that all the atomic orbitals will be in the same orientation, right? So, if I am taking here, this is the orbital, right? This is the orbital plus what will happen here? This is the positive one and again this is the positive one, right? This is spherical and this is like dumbbell shape. According to this idea, you may say like that, plus plus, right? Same phase, there will be overlapping. But according to this zero overlapping concept means that this is in the spherical shape and this is in the different orientation, right? Orientation will be different, so which means that there will be any overlapping. There will not be any overlapping, so it is called as zero overlapping. Overlapping may happen like this, right? Plus plus minus. This is the condition in which plus plus, then in this area it will be plus minus, right? So this will get cancelled, so which means that there is a zero overlapping, right? Clear? The main condition for the zero overlapping that the orientation of the orbitals will be different. There will be different orbital orientation. Clear? Hi, good evening. Aryank. Okay, this is about the orbital overlap concept, about the positive, negative and zero overlapping. So I can say that if you are considering negative and zero overlapping, there will not be any bond formation, right? If you are having any negative or zero overlapping, there will be any bond formation. So we can say that there will be only bond formation in the case of positive overlap only. Clear? Now we are moving to the major part of the VBT or the orbital overlapping considered. We will be dividing the or classifying the covalent bonds into two types, that is sigma bond and pi bond according to the overlapping, right? The first one is the axial overlapping and the second one is the parallel overlapping. What do you mean by axial overlapping? Any idea? Axial overlapping or axial overlapping. If we have any two orbitals, right? If we have any two orbitals, there will be the overlapping just like this. If these are the two orbitals, so I can say that these are overlapping in this head-on way, right? In the axis way. So I can call it as a axial overlapping, and it is formed. The formed bond will be called as sigma bond, represented by this letter. Because the bond is formed along the axis, so it is called as axial overlapping. In chemistry terms, it is called as sigma bond formation, right? Then, yes. Then the second one is the parallel overlapping, right? Parallel overlapping means if these are the orbitals, then it will overlapping like this, right? Parallel. This will be overlapping like this or parallel. That by keeping the axis parallel is known as the parallel overlapping. It leads to the formation of pi bond or represented as pi letter, right? Pi bond. Clear? Now let us see detail about the sigma bond or the head-on overlapping, right? Head-on overlapping. I have already mentioned that in the case of sigma bond formation, atomic orbitals are overlapping in a way that they are along the axis, right? They are along the axis. So, you can see here, this type of covalent bond is formed by the end-to-end or head-on overlapping of the bonding orbitals along their internuclear axis. For example, if I am taking this one, right? I am taking with an example of p orbital. If we are drawing an imaginary line in between the orbitals, this will be the containing the nucleus. This will be called as the internuclear axis, right? Internuclear axis. So overlapping will be happen in between the axis, or the axial overlapping is happen here. So this axis is known as the internuclear axis, right? In the case of sigma bond formation, the overlapping will be happen in between the axis or along the internuclear axis. That is why it is also known as axial overlapping. Clear? Yes. So, in the case of sigma bond formation, there will be different orbitals, right? S orbital is there, p orbital, d orbital is there. So, there will be three conditions for the overlapping. The first one is the SS overlapping. What do you mean by SS overlapping? Which orbital is getting overlapping here? SS overlapping. Two S orbitals, right? Two S orbitals are overlapping in a way that, or the head-on overlapping or axial overlapping. For example, if you are taking the hydrogen molecule, in the case of hydrogen, the electronic configuration is 1s1, right? It contains 1s1 orbital. So, if you am taking two hydrogen atoms, yes, two hydrogen atom, it is forming 1s plus 1s, head-on overlapping, right? This is the 1s orbital, this is the 1s orbital. Then it will form to the axial overlapping or head-on overlapping to form SS sigma bond, right? SS overlapping, or it is a sigma bond. So, we can say that whenever we are drawing the structure, drawing the chemical formula of the hydrogen molecule, H2 molecule is represented as H single bond H, right? Now, you can have the idea about how the sigma bond is forming. Clear? Okay, fine. Now, the second type is the PP overlapping, right? Which means that two p orbitals are overlapping in such a way that they are on the axial position, right? Or the head-on overlapping. For example, if I am taking the case of chlorine molecule, right? What will be the electronic configuration of chlorine? Chlorine 17, right? This is the electronic configuration of chlorine, right? In the case of valence shell, if you are considering this one, 3p5, right? This is the valence shell, it is 3p5. Again, this p orbitals we again divide into px, py, pz, right? So you can write it as 3px, 3py, 3pz, right? 3px, 3py, 3pz. According to our principle, this will be the orientation, right? Here it is 2 electrons, here it is 2 electrons. Only half-filled orbitals will undergo overlapping, right? If you are considering here, it is 3p-Z1 will undergo overlapping in the case of chlorine molecule, right? So as you can see here, 3p, it is along this axis, it will go for the overlapping to form this bond, right? This is our one 3p orbital of one chlorine atom. This is the second 3p orbital of the another chlorine atom. Then it will form the overlapping to form pp sigma bond. Clear? pp sigma bond. That is, whenever we are writing the molecular formula of the chlorine, it will written as Cl single bond Cl, right? This sigma bond is coming from these overlapping. Clear? Yes, fine. Now the next one, the last one of the sigma bond formation, that is the sp overlapping, which means that sp overlapping, which means that one of the s orbital and another p orbital will undergo the axial overlapping or the head-on overlapping. For example, in the case of HCl molecule, right? Hydrogen in the case of hydrogen, it is 1s1, right? So here one electron is there in the case of 1s orbital. And what about here 3p, right? In the case of chlorine, it will be 3p, that is the 3p-Z1. So 1s orbital of hydrogen will overlap with the 3p-Z1 orbital of the chlorine to form sp overlapping, right? It represents the sp sigma bond. This sigma bond formation is responsible for the HCl single bond. Clear? As Aryan, you are right. My next question was that like that. Whenever there is any chance of forming the pi bond with the s orbital. No, right? S orbital will always form. Okay, s orbital will always form the head-on overlapping or the axial overlapping. So it will form sigma bond only. Clear? Now let us move to the second type of covalent bond, right? According to the orbital overlapping concept, that is a pi bond formation. Pi bond formation means I have already discussed, right? There will be the parallel overlapping or the sidewise overlapping. Parallel or sidewise overlapping. Okay, in the formation of the pi bond, the atomic orbitals overlap in such a way that their axes remain parallel, right? Their axes remain parallel to each other and perpendicular to the internuclear axis, right? I will show with the example of the structure. This is our internuclear axis, that is the imaginary line. So okay, this is one of the p orbital having the orientation of this. Then this will be the second orbital, right? Plus minus py orbital, right? It will get overlapping, right? Which means that this is the internuclear axis and these orbitals are along parallel in size, right? They remain parallel to each other. Are you getting? They remain parallel to each other, but it is perpendicular to the internuclear axis, right? Internuclear axis is the imaginary line in between the nucleus. Then these orbitals are parallel to each other, but it is perpendicular to the internuclear axis. That is saying here, in the case of pi bond formation, atomic orbitals overlap in such a way that their axes remain parallel, but it is perpendicular to the internuclear axis. Clear? Then what will happen here? How the bond is formed? positive overlapping, right? Plus plus, minus minus. So this will be the overlapping area. So it will form this is the plus region, this is the minus region. So otherwise we can written it as, or we can draw it as, this is our internuclear axis and this will be the electron cloud. I can represent this as electron cloud having positive charge, positive sign, and the electron cloud having negative sign, which means that the orbitals formed due to the sidewise overlapping consist of two saucer type. We can otherwise draw it as a two saucer type. This is the internuclear axis, two saucer type charged clouds above and below the internuclear axis, above and below the plane of the participating atoms or the internuclear axis. Clear? Sambhav, no need to worry, just prepare for the exam. Anyway, all the best for your exams. Okay, I hope it was clear for everyone. Clear? So I can say that this is the p-pi bonding, right? Two p orbitals are forming the pi bond, so it is calling it as p-pi overlapping, right? Clear? Okay, Nihal, what is the doubt? No? Okay, fine. So, in the case of pi bond overlapping also, there will be some more other conditions, like there will be the formation of overlapping of p orbital with a d orbital, then it will form p-pi d-pi. There will be the chances of p-pi d-pi overlapping as well as d-pi d-pi overlapping. You must have an idea about that, no need to go into the depth. You have this much only in your NCERT textbook. Clear? Aryang, in the case of internuclear axis, if the axis is not mentioned, you will take it as the Z axis, right? Generally, in all the textbook or the NCERT also, the internuclear axis is generally taken it as Z axis, right? Then other axis which is parallel to the Z axis are taken as X or Y, as you wish, right? Clear? Okay, fine. Now, there will be the strength of bonds, right? Now, I have a question for you. If I am taking two bonds, right, sigma bond and pi bond, which will be the more strength? Which will be the most strength bond, sigma or pi bond? By strength wise, which one is most strength? Which one has the more strength, sigma or pi bond? Sigma bond is more stable than, okay, not more stable, have the more strength than the pi bond because of their extent of overlapping, right? We have already discussed about the overlapping in the case of sigma bond, right? There will be the axial, axial, right? Head-on overlapping. There will be the more extent of overlapping. As the extent of overlapping increases, strength of bond also increases according to the postulates of VBT, right? Clear? So, this is the important point from the VBT. Sigma bond is more stronger than the pi bond, right? Aryang, is it clear now? Okay, fine. Now, if we are considering the different orbitals or different energy level, what will be the strength of sigma bonds? We have already discussed that sigma bond is more strength than having more strength than the pi bond. But if we are containing the same energy level, right? What will be the extent of overlapping in the case of sigma bond? We have discussed that there will be three types of bonds, right? SS overlapping, SP overlapping and PP overlapping in the case of sigma bond. Then what will be their extent or their strength? Okay, this will be the extent of overlapping in the case of sigma bond. That is, SS is less, then SP, then PP. This should be noted. Clear? And the point to be noted that it is for the same energy level. If you are considering second energy level, right? 2s is, for example, 2s overlapping. Then 2s 2p overlapping. Then 2p 2p overlapping, right? This is for the same energy level which is in the second orbital, second shell, right? So this will be the extent of overlapping here. Then the next case is that if you are considering the orbitals in the different shells, then what will be their extent of overlapping, right? Yes, that will be the different case, right? Whenever we are discussing about here, we will say that sigma bond is more stronger than the pi bond due to their extent of overlapping because they are in the head-on overlapping, right? Clear? Now, if you are considering the orbitals are of different shells, right? For example, if I am taking 1s 2s and 1s orbital, we can say that the extent of overlapping is maximum in with the lower energy orbitals are present, right? 1s 2s and 1s. This is the lower energy orbital, right? So this will have the maximum extent of overlapping. So I can write like this. Similarly, if I am taking 2s and 2p 3p and 2p 2p, this one have the least energy orbital, right? Second orbital. So this will be the more extent overlapping. Clear? Yes, fine. Now, according to the valence bond theory, we will be discussing about the structure or the structure of the different molecules by using the overlapping concept, right? First, I am taking the example of oxygen molecule. Now, just let me know what is the valence shell or the electronic configuration of oxygen. Electronic configuration of oxygen. 2p4, right? So I will again extend it into 2px, 2py, 2pz. 1, 2, 3, 4, right? Therefore 2, 1, 1. Right? This will be the orbital electronic configuration of oxygen atom. So we can say that there will be the overlapping, right? Only half-filled orbitals will undergo overlapping. So if you are saying here 2py and 2pz will undergo overlapping, right? So I can draw here. For example, I am drawing here. In general, we are taking the internuclear axis as a Z, right? So this will be the pz orbital. Then the second one. This I am simplicity, I am taking this as the py orbital, right? This will be the py orbital. Then what about next? This is the pz orbital, right? According to the electronic configuration, there will be 2 electrons in the case of px, right? Sorry, this is px. Two electrons in the case of px. I am writing here. This will be 2 electrons. Then what about 2py? 2py having 1 electron. Again 2pz having 1 electron. Similarly, the next oxygen is also having the same orbital, right? And what about the next one? If I am taking here, I will just drawing here. This will be our pz orbital or second oxygen atom. Then py orbital of second oxygen atom. My drawing is not perfect. Then again pz orbital of, sorry, px orbital of second oxygen atom, right? This is the pz. This is the py, right? Are you getting my point? So I am filling the electrons here. Again, 1 electron is here, 2 electron is here, then again, sorry, here. This will be the opposite spin, right? This will be the opposite spin. So as you can see here, these two half-filled orbitals will undergo overlapping, right? So this will form overlapping like this. So this is the axial overlapping, right? Which means that there will be a single sigma bond is forming. So we can draw in the case of oxygen, one sigma bond is formed here due to this axial overlapping of p-z orbitals. Clear? Now what about here? These px orbitals having completely filled 2 electrons, there will not be any overlapping. So I am taking here in the case of py orbital, right? Py orbital, there will be the overlapping like this, right? There will be the overlapping like this, and this overlapping is like that. This is in the sidewise, right? Lateral overlapping. So we can say that what bond is forming here? Pi bond, right? A pi bond is forming here. So we can call it as, in the case of oxygen, or double bond O, right? Or double bond O. So the first sigma bond is formed by the axial overlapping of p-z orbital. Then the second pi bond is formed by the lateral overlapping, sidewise overlapping of the py orbital, right? Clear? Clear? So a double bond is formed in the case of oxygen molecule, or double bond O. Now if we are considering the nitrogen molecule, what will be the structure? If we are considering the nitrogen molecule, nitrogen, right? Nitrogen is 7, then 1s2, 2s2, 2p3, right? 2p3 means 2px1, 2py1, 2pz1, right? 2px1, 2py1 and 2pz1. So 2px1, 2py1 and 2pz1, which means that there will be 3 overlapping happens, right? 3 half-filled orbitals are present here. So there will be the chance of 3 overlapping, right? 3 orbital overlapping. So same, I am drawing here. This is our p-z orbital of one nitrogen atom. Then py of the orbital atom, nitrogen atom. Then pz of the nitrogen atom. Similarly, I am drawing the another one also. Okay, what about the electrons here? Both 2ps, 2py and 2pz contain 1 electrons, right? So drawing here 1, 1, 1, again 1, 1, 1. This will undergo one overlapping, axial overlapping to form a sigma bond, right? So if I am drawing the nitrogen here, there will be one sigma bond which is formed by the overlapping of these orbitals, right? This is the p side, this yellow one is the py, then red one is the px, right? There will be the axial overlapping or the head-on overlapping of p-z orbitals to form the first sigma bond of the nitrogen molecule. Then what about the second one? Here, in the case of yellow one, right? That is our py orbital. In the case of py orbital, there will be the sidewise overlapping to form the second pi bond, right? Second bond, that is the first pi bond here. Then what about the third one? Red one, right? Again, there will be again sidewise overlapping of the px orbitals, right? Px orbital, because they contain half-filled electrons. So px orbital, it will form the another pi bond. So if you are considering the nitrogen molecule, there will be 3 bonds, right? The first bond represents the sigma bond and the other 2 bonds represent the pi bond. Clear? Yes, 1 sigma and 2 pi bond. So we can say that a triple bond is formed in the case of N2 molecule. This is the explanation of the structure of the triple bond of N2 molecule according to the valence bond theory. Clear? Okay, fine. Now, these are the major points behind the valence bond theory. We have already discussed about the sigma bond and pi bond, right? So first we have to know the differences between sigma bond and pi bond. We have already discussed. I will just read the table here. First, the sigma bond is formed by the overlap of orbitals along their axis. This is mean along their axis. That is why they are calling the axial overlapping. Then it includes SS, SP and PP overlapping. No doubt, right? We have already discussed. Now, sigma bond is relatively stronger bond due to the extent of overlapping. Then what about pi bond? Pi bond is relatively weaker bond. Then pi bond is formed by the sidewise or lateral overlapping of the atomic orbitals. So it is also known as lateral overlapping, right? Lateral overlapping. Then electron cloud is symmetrical about the internuclear axis, right? If you are taking the SS orbital overlapping, there will be the equal distribution of the electron cloud, right? There will be the equal distribution of electron cloud. So we are called as symmetrical. But if you are considering the pi bond, there will be unsymmetrical electron cloud, but present in two lobes are in the equidistant to the axis. I have already discussed in the case of p pi b pi bonding, right? Clear? Now the substances with the sigma bonds are less reactive, right? Less reactive because they are more stronger. There will be more energy, then it will be less reactive. Then substances with the pi bonds are more reactive, just the opposite, right? Then the last point about the sigma bond is that the shape of the molecule does not described by the sigma bond, while it is explained by the pi bonds. Clear? Okay, fine. So far we discussed about the valence bond theory. We have seen that it is based on the orbital overlapping concept. According to the orbital overlapping concept, it will form three types of overlapping, right? Positive, negative and zero overlapping. This positive overlapping will happens to the bond formation, while negative and zero overlapping does not form any bonds, right? There is no any bond formation. Now, let us see the main drawbacks or the limitations of the valence bond theory. This valence bond theory explains the strength of covalent bond, right? And its directional characteristics also, but it fails to explain the covalency, right? It fails to explain the identical nature of 2 valencies of beryllium, 3 valencies of boron, then 4 valencies of carbon. You will be discussing detail about these structures in the next theory, that is the molecular orbital theory. So this is the main drawback of the valence bond theory. Then this theory also fails to explain the shape and bond angles of even simple molecules like methane, ammonia and water molecule, right? Clear? These are the main drawbacks of the valence bond theory. Even though this explains the strength of covalent bond, but it fails to explain the valencies of different atoms or elements. Then again it will fails to explain the shape and bond angles of some simple molecules. Clear? Yes, that's all about the valence bond theory. Now, according to this, we will be going to with our next theory, that is the molecular orbital theory. Before that, we have to go with another concept, that is the hybridization. Okay, now there is some practice questions for you. The first question is that the type of overlap which is present in the bonds of hydrogen sulfide. What will be the type of overlapping present over there? What will be the answer? Option 1, right? SP overlapping. Okay, what about others? SP3S. Okay, let us see. Option 1 is the correct, sp overlapping. According to valence bond theory, it is sp overlapping. You will be discussing detailing about the hybridization, then we will understand what you mean by sp3, right? It is sp overlapping. What is the molecule given here? H2S, right? H2S, which means that this will be the structure. Maybe this will be the structure in the case of sulfur and hydrogen, right? As we already know, sulfur, there is only, in the case of hydrogen, there is only 1s1 orbital, right? 1s1 electron, 1s1 orbital. So, there will be the overlapping of s orbital is definite, right? There will be overlapping of s orbital there. Then what about the sulfur? Just calculate or just find out the valence shell of the sulfur. Sulfur is having this is like neon after 3s2 3p4. Neon is 10, 10 plus 2 12 plus 4 16. 16 sulfur, which means that 3p orbital of the sulfur will undergo overlapping with the 1s orbital of hydrogen to form the orbital or the bond in the case of H2S molecule. Yes, H2S molecule. So we can say that the overlapping will be sp overlapping, which means option 1 is the correct. Clear? Clear? Okay, Aryan, I will discuss detail about the sp3 hybridization, then you will get the answer for this, right? The next session, tomorrow. Why it is not a sp3 s orbital overlapping. Clear? Now, here is the next question. Choose the molecule which has only one pi bond. Only one pi bond. We have an idea that whenever we are having double bond, right? One will be sigma bond and other one will be pi bond, right? One is sigma bond and other one is pi bond. Then if we are having a triple bond, right? Which means 3 bonds are there. One is representing the sigma bond, one is representing the sigma bond, then other 2 are the pi bond, right? These are the basics. Then molecule is given here along with their bond structure. You just identify which molecule has only one pi bond. Now read the question carefully. There will be mistakes happen. Question is, which one having only one pi bond? Hi Girvar. Option 3, right? Option 3. As you can see here in the case of first option, this is one pi bond, this is one pi bond, right? So there are 2 pi bond in the case of first example. Then what about the second one? By looking at the structure only, we will be making confusing that there will be only one pi bond. But as you can see here, if you are familiar with the structure of C double bond OH, right? This is the structure of carboxylic acid. This means C double bond, there will be a pi bond also, right? So here also it is having 2 pi bond. Then what about the third one? CH3, CH double bond, CH2, right? In the case of the double bond, one is sigma bond and other one is one pi bond, right? Clear? Then what about the last one? Triple bond, right? One sigma bond and 2 pi bond. Clear? Option 3 will be the correct answer here. Hi Aditya and Parth. Okay, this is the next question. Then predict the nature of bond, and it is given that the type of orbitals, and this axis will represent the internuclear axis. This axis will represent the internuclear axis. You have to predict the bond, whether it is sigma or pi bond. Whether it is sigma or pi bond. Okay, I will just give the answer of first question, that is the S plus S orbital overlapping. So, for example, sigma bond, right? If you are considering the SS overlapping, there will be always sigma bond formation, right? There will be always sigma bond formation. So, what about here? S plus Px orbital, right? S plus Px orbital. Okay. Our internuclear axis is x-axis here, right? Internuclear axis is x-axis here. So, if I am taking here, this will be our axis, that is the x-axis, right? Okay, this will be our s orbital. Then px means the orbital along the x-axis, right? So, this will be the px orbital. This will be the px orbital. Right, this will be the px orbital, this will be the s orbital. What will happen to the bond here? Whether it is sideways overlapping or head-on overlapping. Whether it is forming sigma bond or pi bond. That is the question. Head-on overlapping, right? Head-on overlapping, which means that it will also form the sigma bond. Clear? Is the thing clear? Okay, what about the third one? Yes, head-on overlapping, right? Okay, what about the third one here? Here the internuclear axis is given that it is y-axis, right? This is our y-axis, that is the internuclear axis. So, if I am taking here y-axis, then first orbital it is s orbital, right? First orbital it is s orbital. So, I am taking here, this is our s orbital. Then, what about the py orbital? Py orbital means the p orbital which is lying along the y-axis. It is in the same side, right? So, it will again undergo head-on overlapping to form sigma bond. Clear? Clear? Now, just give me the answer about the fourth one, whether it is forming sigma bond or pi bond. S plus Px, which is given that internuclear axis is z axis. First, you have to draw the internuclear axis and make it as z axis. Then draw the s orbital and px orbital. Then just check whether it is having the overlapping of head-on overlapping or sideways overlapping. That will be the answer. This is the z axis, right? This is our internuclear axis. Then, this is the s orbital. Then, what is the orbital overlapping here? Px orbital, right? Which means that internuclear axis is z axis, but px orbital is perpendicular to it, right? So, I am drawing here perpendicular to here, which means that there is no any overlapping, right? Yes, you are correct. It is zero overlapping. Or we can say that there is no any overlapping, no overlapping. Aryank, you are correct. Now, what about the next one? Fifth one. Again sigma bond, right? This is the px orbital. Again it will undergo the head-on overlapping to form px sigma bond. So fifth one is again sigma bond. Then what about the sixth one? Sixth one. Py orbital is perpendicular, right? Py orbital is perpendicular. So it will form the sidewise overlapping, right? Sidewise overlapping, right? So we can say that in this case it will form pi bond. Clear? Pi bond. Then what about the last one? Seventh one, right? Internuclear axis is x-axis. So drawing the internuclear axis here. Orbitals are p set, which is along the, if the internuclear axis is x, then other two orbitals are perpendicular to each other, right? Perpendicular to the internuclear axis. So I am drawing here p set, right? Again, sidewise overlapping, it will form pi bond. Clear? The last one, it is forming pi bond. Clear? Okay, Parth, what is your doubt? Is it related to this? Okay, Girvar, in the case of px overlapping, overlapping, right? Here, right? Okay, here it is px overlapping, which is means head-on overlapping, right? They are forming the head-on overlapping, which means that in the case of head-on overlapping, we will call it as a sigma bond, right? Clear? If you don't have any, I mean you didn't get this, you just watch the recorded session of this particular session. I have discussed detailedly about this overlapping in this particular session. Okay, this is all about from my side for today. We have successfully discussed about the valence bond theory. This valence bond theory is mainly based on the concept of orbital overlapping. According to the overlapping, there will be three types of overlapping, right? Positive, negative and zero overlapping. Only positive overlapping will happen to the lead to the formation of bond. Then if you are considering the types of covalent bond, according to the orbital overlapping, there will be two types of bond, right? One is sigma bond and other one is covalent bond, right? So we have seen about how to draw the structure of different molecules according to the valence bond theory. Now we have practiced some questions also. I hope it was clear for everyone. Okay. Anyway, the gentle reminder about the All India test series. Again, this test series is for the 299 having the coupon code of YouTube 50 off. So don't miss it. Just enroll now. Now, the next session, I mean tomorrow, I will come back with the hybridization concept, which is the more important concept according to the valence bond theory. So you will get the idea about how the shape of the molecules are forming or the geometry is changing, right? So be ready for that. Till then, bye bye all of you. Thank you so much. Then don't forget to subscribe our channel. Do like and share this particular session to your friends and family also. So till then, bye bye.